Good morning. Am I audible?
Yes, sir.
Okay. So let us get started. Is it visible now?
Yes, sir.
Good. So, friends, good morning again. Welcome to the next discussion on UML. So, we have been discussing about sequence diagrams, which are very important behavioral diagrams for mapping the temporal sequence of events in the overall client-server framework of a system. So we saw that sequence diagram has certain components. One, the most important being the lifeline, which is the lifeline of an object as it stays in the system starting from the time it is created to the time it is deleted, and is shown by typically by a vertical line with a box on the top which describes the object. It could be named or unnamed or indexed. And then between the along the timeline, objects send messages to objects on other timeline, or can actually send a message to create an object. So this message passing is a basic property of the sequence diagram, and the order in which the messages happen on the timeline from top to below is the sequential order of things that would happen. And we have also noted that most often this is just a sequential order. This is not a timed, clocked diagram. Like there's a difference between a sequence diagram and a timing diagram. This is not a timing diagram. Timing diagram will have more of the real-time constraints and so on, the timing dependencies and so on. Here you are just talking about the sequencing of events, the order of events. Of course, it is possible at places to give some timing constraints, but significantly remember that sequence diagram is about conceptualizing the ordering of actions that must happen, ordering of messages that must happen in a system. So we looked at the lifeline and messages. The third, which is, pretty much obvious, is the interaction fragment. The way the messages interact on in the sequence diagram. So we'll just take a quick look into that. These are examples that we have seen. I'm skipping over. Going to slide 7 on module 30. So interaction fragment is a named element representing the most general interaction unit, and there could be many of that. Each interaction fragment is like an interaction by itself, kind of. There is no general notation for it, but every type of interaction has a notation of its own. So these are the most widely used types of interaction fragments: occurrence, execution, state invariant, and so on. So occurrence is an interaction fragment which represents a moment in time, right? Again, not the clock time, but a moment in time, an event at the beginning or end of a message, or at the beginning or end of execution. So this is an occurrence. This is occurrence of this is a message occurrence. This a message is being sent, or this message is being received. This is the cross out is another occurrence. The denoting the destruction of the current instance and kind of closing of that lifeline. An occurrence, start occurrence where the execution starts. This is a finish occurrence where the execution ends. This is the execution occurrence itself. So these are the different, happening of different events are occurrence interaction fragments in sequence diagram. Pretty obvious in notion, but just formalized. Then we say that execution or activation itself is an interaction fragment which represents a period in the particular lifetime when it is executing a unit behavior or action with the lifeline. That is as it is doing here. Executing a unit behavior or action within that lifeline. It may be sending a signal to other participants or waiting for messages from other participants. Right? Both of these are possible. Right. So typically we show it by a thin gray or white rectangle on the lifeline. Or there are blocked representations for execution interaction fragments, execution interaction fragments also, like is a search. So you're not going into the details, but the level identifies that action. So these are the different ways. I mean, pretty much what happens in the context of a given diagram, pretty much it becomes clear from the context, but you will need to know this notation and meaning in order to be able to create your own diagram. So execution fragments could be overlapped. We have seen this before also, like there's execution going on and there's a occurrence happening here, the execution start occurrence, and this execution is overlapped on the earlier one. Or for that matter, service had sent a start request to task which was non-blocking. It continues, and task then needs some computation done from the service. So it does a callback which is blocking, and which is an overlapped interaction segment, overlapped execution. So service does that and replies back, and only after that task can continue and finally respond back. So these are the other kind are to denote state invariance. That is interaction fragment which can put a runtime constraint and the participants of the interaction, and different kinds of constraints, internal, external. For example, this could be based on an internal state. So you say that this is to be done if T attribute T equals complete, then. Or you could say that this is goes on, and at the end of so this continues till T becomes complete. This continues till the task reaches a state which is finished. Right. So this kind of state invariant annotations are possible, which are called state and invariant interaction fragments. Right? Then another kind of is interaction use. This is particularly done for higher level abstraction. For example, checkout by itself may be a big sequence diagram, the checkout process of an item, say on Bull Luggage store. So here you say that this is how the interaction is used. So the web customer and online bookshop, they refer to the interaction checkout. The reference could have some parameters also. So these are interaction use as a fragment. So you're saying that this interaction is used, but it's not detailed here. So there, by name, there'll be somewhere else where a large and complex sequence diagram for them would be detailed out. But here you are just referring to it so that the current part of the interaction, current part of the sequence diagram can make good sense. So we have seen different kinds of interaction fragments, starting from occurrence to execution to state and so on. So here are some of the annotated examples. I think you have seen all of this. This is a sequence, synchronous message, return message, all that. This is, for example, you had seen this. We had not defined handle errors at that time. This is a interaction use. So there are a lot of things that will happen here, but we have simplified here by just saying handle errors. So there'll be a separate sequence diagram to detail how to handle errors. This is, for example, an occurrence specification. This is object creation and so on. This is a destruction occurrence and so on. Facebook authentication, which I asked you to study yourself. So I'm sure, just one second. Okay, so some for the leave management system. So you can try to do that and see. So I'll not go through these. You can go through them and make out for yourself. So that was for the sequence diagram. Actually, you'll get to practice. Uh, one second, one. Okay, so that was about the sequence diagram, which we will get to practice in the upcoming assignment. So now let us move on to the next behavioral diagram. So far we have seen the use case diagram, the class diagram, and the sequence diagram. So the use case diagram at the behavioral level is a top-down one about uh, the about the overall capture of the requirement specification. Class diagram we saw at the more detailing of the classes, and finally the sequence diagram is kind of the temporal ordering, sequencing ordering of the events, messages that will happen in the system. Right? Now, we next talk about a variant of this as a behavioral, which we call the communication diagram, which will also have frame, lifeline, and messages. So let us. So this is in terms of overall what it is. So what is written as collaboration diagram here is currently later on has been renamed as communication diagram. So this collaboration or communication diagram is the next to see, which takes place in the analysis phase as well. So let us understand that communication diagram is also a UML behavioral diagram. It depicts inter-object behavior, and note this part is important, ordered by space. In terms of sequence diagram, our focus is in terms of the ordering of the messages, sequencing of the events. And in that process, whoever participates in that happens to be on that timeline. So the primary goal, you remember that our whole idea of this modeling is based on the fact that at any point of time, we focus on one aspect that we want to detail, and we kind of ignore the rest or put them as less relevant, and the remaining we just ignore and so on. So the sequence diagram is trying to look at the order in which messages are happening. Naturally, messages happen between objects, but objects are not the primary item here. They're incidental because of the messages, the ordering of the messages which are important for the sequence diagram. In communication diagram, you kind of take a different look. You look at it by space, wherein you say that these are the objects. Let us see what are the messages they exchange between themselves. Now, you are not looking at the ordering of those messages in the primary way. Like in sequence diagram, when you are looking at the ordering of the messages, also incidentally, you will always know what the object is, otherwise who is sending and who is receiving and so on. But they are not the primary focus. The primary focus is the ordering sequence of the messages. Here in communication diagram also, Your sequencing of message in some way will be there, but your primary focus are the objects. What are the objects in my system? And for every object, what are the messages that it sends out to other objects? And then you put some annotation to mark what is the ordering and so on. Right? So let's take a look. So the major components in the communication diagram are frame, lifeline, and messages. Messages are still there, but the notation for each one of them would be somewhat different. So communication diagram is typically shown within a rectangular frame, and you write a name at the in the compartment in the upper left corner. The frame is almost uniform for all kinds of UML diagrams actually. And there could be a shorter form of that. So you say interaction by item or SD by item, short frame by item, more abstraction. You have lifelines, but the difference from the sequence diagram is in sequence diagram, you show the lifeline as a line coming from top to bottom, continuous or hashed, whatever. It has a tail. This line is called the tail. So as if the head is the box, the object, and so it has a tail. So, but in the communication diagram, you just have the head. You do not have this tail, right? So colon user is the lifeline of an anonymous class user object. Data colon stock is the lifeline of data object of class stock. Similarly, the indexed objects and so on. So the concept is the same. So lifeline, it's called lifeline because naturally, if an object has to participate in the system, it has to be alive. So it must be in that lifetime. When you have messages, here messages have a little different form. Messages naturally have an arrow. And since you do not have the tail, the messages go directly between the lifelines denoted by the boxes. So it's a link between them. The link has an arrow showing the direction of the message flow, and you have a sequence expression. The sequence expression says what is the message and what is the condition of the message and what is the annotation of the message and so on. So here, let us read this out. I'll come to the syntax subsequently. So just an initial example to get started with. So what this is doing is an anonymous instance of class A is sending the message to an anonymous instance of class B. The message is remove. Sends the remove message. Right. This has a guard condition. This is called a guard condition within square bracket, which is S1 dot equals S2. So if S1 is equal to S2, then you send this message. So that is a guard condition. And this is the identification of the message or the annotation of the message. Let's see what it means. So first, let us look at this annotation or sequence expression. Sequence expression is a dot separated list of sequence terms. So kind of they say that if you think in the sequencing form, that is in terms of ordering form, then these numbers denote the time forward order of messages happening, right? And then sub order in terms of that. So let's get more into. Let's say this is an example. So a sequence expression has this form: sequence term dot 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 dot. So sequence term is like this, and the sequence term is integer like 3, a name like AB, and then recurrence. You keep on happening. So this is a sequence term dot, so on. Continues till you have a colon here, and then you have the message name. M5 is a message name. So the sequence expression is 3b.2.2. Message name is M5. Here the integer represents the sequential order of the message, within the next higher level of procedural calling. We'll explain. This sentence does not mean much. So we say that message with sequence 2 follows message with sequence 1. All messages that has a sequence expression starting with 2 will happen after all messages that start with a sequence expression starting with 1. 2.1 will follow 2. 5.3 will follow 5.2 within the activation of 5. So it's kind of a subroutine call, you can say. 1.2.4 will follow message 1.2.3, and both will be within the activation of 1.2. So you can see one is ordering within a level and another is going inside a level, right? So when I go to the next decimal level, I'm going inside that activation level, and when I have sequencing numbers within one position level, then they are the order in which. So if I have A sending a message to B, draw message to B, and B sending a draw message to C, by the numbering I can say that this message goes before this message goes. 1.2 colon draw will go before 1.3 colon draw, right? So first A sends a draw message to instance B, and then after that B sends a draw message to C. The name, on the other hand, this was about the numbers. The name, on the other hand, represent concurrency or concurrent thread of control. So 2.3a and 2.3b are concurrent within the activation of 2.3. So here there's no ordering. If I had said 2.3.1 and 2.3.2, then this would have happened first, this would have happened next. But here, no. It is 2.3a, 2.3b. It means it's concurrence. Both happen at the same time, right? So A, B, etc. The name represents that they are concurrent. So 1.1. So 1A, 1B will be concurrent in 1. 1.1 is after 1. It's within 1, right? So that will follow 1A, 1B. 3A.2.1, 3B.2.1 in the same way will follow 3.2. That's the kind of interpretation for this notation. Okay. The other parts of the sequence expression is the guard. I briefly mentioned earlier that after the sequence expression, I can, in square bracket, I can put a Boolean condition which say that the message draw will be executed if X is greater than Y, or this message 1.1.1 of remove will be executed if S1 equals S2. So these are the guard conditions that we have. Then we can repeat a certain message which defines conditional or iterative execution of 0 or more messages. It could branch, loop on a guard condition. So star necessarily means that it is a recurrence which is sequential. That is, the message is repeated but sequentially. That is, after one message ends, the second message will start, and then the third message, and so on. And this is concurrent, where messages are executed concurrently at the same time, right? So let us see 4.2.4.2c. We are saying star 1 is equal to 1 to 12 search ti. Right. So it's a search message for ti. It will be executed 12 times, one after the other. So first you'll have search t1, done, you'll have search t2, done, you'll have search t3. In this way up to search t12. But if you do star parallel this, Then you'll have search TI. So all 12 such messages will be sent out at the same time, concurrently. Right? There could be unspecified repetition, like star notify. So notify will be repeated some unspecified number of times. Right? So this is the, so these are depictions of some recurrence and iteration. I mean, what we have just written as expression is in terms of the diagram, as you see. So let us try to interpret this communication diagram. So as I said, communication diagram is in space. So what primarily you're trying to show are 1, 2, 3, 4, 5 lifelines. That is 5 objects. Online bookshop, inventory, book, shopping cart, order. And these are messages that are sent from one lifeline to the other. We have layered them in terms of numbering. So 1. So 1 is sent from the user to the online bookshop. This message is find book. And the user tries to find book arbitrary number of times. So it is star. Then in 1.1, after this, there are 1.1, 1.2, 1.3. So the next what happens is 1.1. 1.1 search goes to inventory. Right. So every time you do a find book, you search inventory. Then happens 1.2, but what is being implicitly shown here without details, because our aspect currently is looking at messages between objects, not the details of algorithm, but what is related here is the fact 1.2 interested. So it means that the view book message will be sent only if there is interest, right? So search, after that says some interest shown, and that goes to the book. So you can get to see the book. Then again, you may again start doing find book from here. But if you decide to buy, then decided to buy, then 1.3 goes out to the shopping cart. Then you send add to shopping cart message from the online bookshop. So by this flow or exchange of messages, this is not exactly a flow. Some of them will happen, some will abort, again come back, restart in this way. But the final end of this round 1 of messages certainly is when it ends up in the shopping cart. And you start the next round, which is numbered as a different activity, checkout. So 2 is a checkout that the user starts on the online bookshop. Naturally, what do you need to do for checkout? You check on the shopping cart. So you get the books from the shopping cart, 2.1. Now there will have to be something in the shopping cart to be able to make the order. So that is the guard condition, not empty cart. If the cart is not empty, then you make the order, otherwise you can't. So 2.1 is make order. And once this is complete, order complete, then which, I mean, payments and those details are not really shown here. But once this is complete, then you update the inventory for the order 2.3. So this is typically how a collaboration diagram will look like. This is the annotated form from UML 2.5 website. So I'm sorry, that's I missed out. This user is also there. So there is a 1, 2, 3, 6 lifelines are there. So this is a find book. This is the sequence expression, the iteration, the message, the guard condition, the lifeline name, Here they've given a lifeline name. Here given a selector name that is to be a customer, and so on. The sequence expression here. There's a frame, the type of diagram, and the frame heading, the diagram frame as a whole, and so on. So that's typically a communication diagram that you are getting to see. Here is another given as an example, which I'll leave to you to understand and follow better. So what we presented in brief was a communication diagram. So we have seen one kind of top level behavior diagram, which is use case, pretty abstract. We have seen pretty much of a detailed structural diagram in class. And then we have seen in the context of a generic client server model, we have seen two kinds of messaging diagram. One is temporal messaging in terms of sequence diagram, and one is spatial messaging in terms of the communication diagram. So before I get into the activity diagram, let me see if there are questions. Any questions, friends? No questions? You all are too smart, right? So let us get back. Let us try to talk about another behavioral diagram, which is, so here we have just been so far been showing at the level of message abstraction as to what goes between objects either in time order or in the space order. Now we will next focus on what are the activities, rather a little bit more on what are the algorithms that take part in terms of the system design, which is called the activity diagram. So the activity diagrams have a lot of things: activities, partition, activity age, control, object, action. Let us look at those one by one. So this is just kind of showing some of the activities at the high use case diagram level. So let us see what it says. It's such a group check-in, individual check-in, and baggage checking. So it's a use case diagram which is showing you different kinds of checking. So a passenger can do an individual check-in, where baggage checking extends that, because someone can do an individual checking without doing a baggage checking, but the individual checking may be extended by checking your baggage also. So extend relationship is there, which is quite clear. Then if there is a tour guide conducting a group tour, then the tour guide can do a group checking. But group checking will mean that individual checking for every group member, so it includes individual checking. And the tour guide is a passenger, right? There's a generalization between the actors, the association. So these are the different activities, and then every passenger has to do the security screening. So these are the different kinds of activities that happen. So now we are more interested to blow up and look into this kind of inside of these kind of activities, not necessarily the checking in activities, but maybe something similar. So in terms of the overall scope of diagram, this is where it happens, is activity diagram, one of the behavioral models we have seen in class, sequence, not collaboration, the communication diagram and so on. So activity diagram is a UML behavior diagram which shows the flow of control or object. So it's kind of, it can get activities, or activation can happen on control, or it can happen on data. Right? Both are possible. with emphasis on the sequence and conditions of the flow. Right. It has to happen in the right order. And obviously, there will be guard and preconditions in terms of that. They look like flowcharts, but they are generalizations of that. If you think about flowcharts, then flowcharts only show you the control. It does not show you the data, triggering on data. I mean, it does not look at the availability of data and so on. It always assumes that the data is there and how the control is flowing. So you will see later on also in other context, particularly when you study compiler, you will see that we will talk about data flow diagrams or data flow graph, or we will talk about control flow diagrams or control flow graphs. So how control flows and how data flows. Then we'll have control and data flow graph and so on. So activity diagram is pretty much like that. Now, so as I said, that it is typically used to model an algorithm, right? Activity. Activities at the end of the day is finally in your system is going to be an algorithm. So it could be sequential as well as concurrent or parallel. And certainly the target, as I showed with that booking sample example, is to realize use cases. They have activities, and how do you realize them? So kind of a sample activity diagram. You are creating a blogging account, the initial node. So typically in an activity diagram, this black dot, big dot, means the start of the activity. And this black dot within a circle means the end of the activity. Otherwise, the arrows mean natural control flow, right? Diamonds are condition checks or used as join or merge points. Like in flowchart, we simply will put these lines together, but no, here we recognize that there will have to be a join here. There's a two control flow that are coming, and that is required because when flowcharts were done, the entire world is in the sequential view. So when two control paths merge at a point, the semantics necessarily is exclusive. Because it is sequential, naturally that part. So there is no merging that is required. But the moment you get into concurrency or parallelism, it is possible that two branches could be executing in concurrence, in parallel. So when they meet at a point, there needs to be a precondition, the condition check as to is it okay to go forward if one has reached there or both needs to reach there and so on. So you need a node. So that's a diamond node. With the hashed lines, you put certain kind of annotation. Right. So this is the initial node. This is an edge. Ask system to create new blog account. That's the first action. Then select account type. So these are different actions being taken, activities being done, and it's just from one activity to the other. It's basically a control flow that's happening. Select account type. Enter author's details. Whoever wants to do the blog. Verify author details, and then you have a condition checking here, which is based on a decision. So there may be a separate activity diagram which gives you that decision. I mean, what are the parameters to decide and so on. But the outcomes are shown here. It is authorized or not authorized. Not authorized, the action is reject application. Authorized, create new blog account, email blog account summary to the author. And in either of the case, you come here. Here it is exclusive branches. So only one of them will activate. And then you merge at this point as is showing, and is a final node event. So this is a very rudimentary and almost your flowchart like form of an activity diagram, which is based on the control flow. Right. The actions coordinated by activity models can be initiated because, so what initiates an activity? Because other action finish executing. This is what the flowchart does. And this is what we saw in the last diagram also. but it could be activated by object and data becoming available. Right? Maybe the control was already there. You can say I can start going any point of time provided I have this data. The printer is ready all the time. It starts printing as soon as it gets a file. Right? So it is more than a rather than a control flow, there is a data flow issue that the printer does not start printing activity because it does not have the data to print. Right? So it could be an activity could be triggered by an object or a data, not necessarily by control, which is the first one. And some event external to the flow occurs. It may be due to something which is outside of this flow, which is not coming from this flow. Right? Some external input, some interrupt, something. Right? So these are what the activities can do that. And the major components of the activity diagram are activity, partition, activity edge, control, object, actions. There's no point reading them out. We have to see them one by one. Okay, so activity. Activity is a parameterized behavior represented as coordinated flow of actions. So activity is not one thing. It's a behavior. It has a coordinated flow of actions. That is well-designed flow of actions. And it could have parameters. So you're saying that this is an activity. Online shopping activity. These are all different actions. This is a start, this is an end. These are all different actions. And there is a coordinated flow. Starts here, goes here, like that. This also is another, which is authenticate user activity. And this is parameterized. So it's if I have to do this activity, then I need a login, which is a string. I need a password, which is a string. So login ID and password. Right? And then this activity can happen. So this is coordinated flow of actions is the activity. As a behavior, activity could have precondition and postcondition constraints. And those are marked as within limits as precondition and postcondition. Like in here. So you have a vending activity. So in the vending machine, the precondition of vending is exact change must be provided. The postcondition is the item that after you have done that, you have to say what that item is. Only then the vending can happen. Right? So only then the item will come out, not the vending. Vending outcome can happen. So the postcondition is an outcome will happen. The precondition is change has to be given. Right? So you can specify those in the activity. Then activities can be partitioned into groups for better understanding. Like it could be in terms of organizational unit or business model and so on. They are typically shown as swim lane notation. You have seen swimming pool, right? Divided into swim lanes through which the swimmers participate. So those are this kind of. So these are swim lane notations. So it could be horizontal, it could be vertical. So this shows activities of customer will be shown in this swim lane, activities of order will be shown in this swim lane, and so on. That helps to understand and keep organizational things similar in that way. So some activity could be external. So it has a Guillemot saying external, right? Then activity can have ages. So
Sir, you are not audible.
Sorry, I had lost the connection. I'm back now. So we are on to slide 15. So activity age is an abstract class for directed connection along which token or data objects flow between activity nodes. So you can say that this will be activated along this edge. So it could be just a control edge like this: fill order, then order update, or update order, and then update order will trigger review order if it is updated, right? So the edge updated. Or there could be objects that flow along the edges. We typically say tokens, which will trigger the activity. Now, activity edges may have different attributes. For example, there could be again a guard condition. I say that priority 1, priority equal to 1. Only then this fill order will happen. Otherwise, this edge will not activate. That is, the activity will not start. They could use connectors. This is very typical in flowcharts also. You can use a connector here. You can have object flow edges, as I said. That here, earlier we just did flow order going to review order. But now we are saying that flow order has an order. Look, it's drawn in rectangle, so it's an object now. And that goes into the review order. So it is not the control, but this is the object flow edge. So flow order, fill order generates an order which goes into the review order, which is logical. Otherwise, what do you review? Or you could have, very passive object count. Like you say, I say wet is equal to 6. Note, this is written in curly braces. In square bracket, it would have been a guard condition. Here, what it means is wet is 6 is, so there are warning tokens coming from send warning to send notification. So wet is saying that the minimum number of tokens that must traverse this edge at the same time before, so that the send notification happens. So it's not that every time you get a warning and you send a notification, then the system will get very noisy. So if the number of warnings reach 6, then you will send the notification. So these are kind of object flow edges that can happen between activities, right? There could be interrupting edges more for depiction, like cancel request. You have canceled the request, so it has to cancel the order, typically shown as zigzag. So here, summarizing, you have a online shopping. I'm sorry, online shopping. So at any point, let us say that you start here, right? This is the start point of the activity. So you come and you have a choice to do either search or browse. If you do search, you will search items. If you do not find, you come back and search or browse again. If you browse, similarly, you browse item. And if you found, then you go and view the item. You do that on finding a search output also. So this node kind of depicts that you have found an item either by searching or by browsing, so that you view the item. And then you make a decision. If you have made the decision, that is kind of, if you want to buy, then you proceed. Otherwise, you come back to search or you come back to browse. Again, you have a choice, because like you have a choice here. You have a choice at this point, right? Now, then you add to the, if you have made a decision, you add to the shopping cart, right? Then you proceed here. You can view the cart. After viewing the shopping cart, you may need to update. So you update and go back here. And if you are done with the shopping, then you go to C. Otherwise, if you have to do more shopping, you come back to B. So these are the continuation notes. You come back to B and again you do this. Otherwise, you go to C, you proceed to checkout and you check out the item and you are done. Right? So independently also, shopping cart can be checked at any point of time. You can check here, directly come to this, not linked to your finding out an item and so on. Right? So that's kind of now showing you. Earlier we have seen different, kind of messages going between different objects and so on. Now we are seeing in terms of activity, actually what is activity that's being done by the user on this system. This is the swim lane diagram for ticket vending machine. So you have 3 swim lanes on customer, ticket vending machine, and bank. Right? So these 3. So that was about the first part of the activity diagram. We have only 5 more minutes. So let me stop here. I'll continue on the remaining of the activity diagrams tomorrow. Just let me check if there is any question. So we have completed the discussion on the sequence diagram, particularly the interaction fragments, taken a look at the special message diagram, which is a communication diagram. And we have done on the basic part of the activities diagram, which is the simple part. We will have some bit more of signaling and all that when we discuss tomorrow. Any question, friends?
Sir, our activity diagram is essentially an expansion of the use case diagram. Because, like, the way
Yeah.
I'm seeing it is that in use case, say a actor wants to do something, and so we have those use cases, and here we're expanding that use cases to steps.
I mean, it's a completely different level. Every use case may become multiple activities diagram. Actually, use case is just an abstraction. I want to buy an item. I want to order an item. This kind of. And then here, of course, they're related, because that's how you are detailing. That's the whole process, right? So in terms of use case, as I always referring to, it is the highest level of abstraction in terms of your behavior, but it does not tell you how, by whom, when, and so on. So you're using different diagrams to say that. So sequence diagram has tried to say the temporal order. Collaboration communication diagram is trying to say the spatial order of interaction. Activity diagram is very specific about algorithm. Right. So it is an expansion, but it's a significant expansion, so that not much reason to directly refer it to. But obviously, if you have use cases, you will have activity diagram corresponding to them, and vice versa. But you may have some activity diagrams which are parts of things which are not shown as use cases separately, but you are needed for the other activities. Does it make sense?
Yes, sir. So, like, activity diagrams, so basically, it is a more sophisticated flowchart. The way I understand, like, when you have the swimming pool
Yeah,
lane.
that's what I said. But the difference is a flowchart is a control flow graph, but here you have a control data event flow graph. So
Yeah.
it's a more generalized form of that. Right?
Yeah.
Because with a control flow graph, you cannot represent a whole lot of dependencies in the real world, because in several times activities will have to wait on events happening, on data arriving, and so on.
So
So
you
that's
can't
not
have
control.
joins in a
Yeah,
flowchart.
yeah. And then the other is flowchart is necessarily a sequential mechanism. So flowchart is not amenable to expressing concurrency and parallelism, which is certainly you want to represent them in your UML diagrams to be able to later on translate them easily in your HDL, HLD, and LLD easily. And as a chain of that, at the end, we will see the state machine or state chart diagram also, which will try to take it little closer to, can you have a state abstraction on the whole problem, so that you can encode it very easily in your algorithm. Right.
Thank you, sir.
Welcome. Welcome. Any other question? No. Okay. Thank you then. Have a nice day. See you again tomorrow. Bye.